fluid mechanics. Okay, so fluid mechanics is that branch of science which deals with behavior of fluids. Fluid could either be a gas or a liquid. So it deals with behavior of fluid at rest or in motion. What then is a fluid actually? A fluid is a substance that is capable of flowing, or you say a fluid is a substance which deforms continuously when subjected to an external shearing force. Like I said, a fluid can either be a liquid or a gas. Now, we want to look at the various properties of fluid, and these are the properties we want to consider. 1, density. 2, specific volume. 3, weight density. And 4, specific gravity. So let's look at the very first one now. Density is also known as mass density. Sorry, this is a mistake. Mass density. And so it is defined as the ratio of the mass of a fluid to its volume. It's also known as specific mass. So you can say mass density, so you can say density, mass density, or specific mass, and is measured in kilogram per meter cube. So density is mass over volume. Now, the next one we have is the specific volume. The specific volume of a fluid is defined as the ratio of the volume of a fluid to its mass, or you say it's the volume occupied by a unit mass. So, specific volume, V subscript S, is given as volume over mass. It is measured in meter cube. You can see meter cube over kg. So, meter cube per kg, that's the unit. Now, understand that density is mass over volume, while specific volume is volume over mass. These two are inverse of one another. We can say that specific volume is 1 over density, or you can say density is 1 over specific volume. The next property we'll talk about now is the weight density. Okay, it's also known as specific weight, and is simply the ratio of weight to the volume of a fluid. Weight density, written with represented with W, is weight over volume. But remember now that weight is mass times acceleration due to gravity. That's mg, m for mass and g for gravity. If we substitute that into this, that will be mg over volume v. Now we can separate this by writing that m over v times g. But remember that mass over volume is density. So there's a relationship now between weight density, and that's the fact that weight density is density times gravity. So we're taking the last one now. So specific gravity, that's the last property we want to consider. Specific gravity is defined as the ratio of the weight density of a fluid to the weight density of water. Specific gravity, like I said, is specific weight of a fluid divided by specific weight of water. So represented with S. But we know that specific weight of water is a constant actually. 9,810 Newton per meter cube. So we can say specific gravity is the specific weight of the fluid over 9,810. Now, specific weight also, we proved that earlier, that it is density times gravity. That specific weight or weight density has a relationship between density and gravity too. So, and this is the relationship. We defined that earlier. So we can come back here to say that specific weight of a fluid will be density of the fluid times gravity, and specific weight of water will be density of water times gravity. Now, if we eliminate G, because G is constant, 9.81, that what will take the value of G to be. So we'll be left with density of fluid over density of water. The density of water is constant. That's 1,000 kilogram per meter cube. That's the density of water. Now, we can therefore say also that specific gravity is density of fluid over 1000. So understand that there are two relationships for specific gravity. Now, you see this word specific is so much here that you might want to confuse them, but don't confuse them. We've done three things. We've done the first one, specific mass, which is also known as density or mass density. So specific mass, that is mass density or density, and that's mass over volume. We also do specific volume, and that's volume over mass, which is the inverse of density. We've also done specific weight, which is weight density, and that is giving us weight over volume or density times gravity as proven here. And last one is specific gravity. So the specific, you need to look at this and keep recalling them so you don't make mistake. But again, like I said earlier, that specific gravity has two relationships. You can use specific weight or weight density to relate specific gravity, or you can use density to relate specific gravity. Any of this would work, either using specific weight or using density. So let's look at this example now. Calculate the specific weight, okay, specific mass, this means density, and specific volume and specific gravity of a liquid having a volume of 6 meter cube and weight of 44 kilonewton. So let's solve this question right away now. A very quick one. What are we asked to get initially? We're asked to get firstly specific weight. So specific weight W is weight over volume. In this question, we are given the weight 44 kilonewton. I need to convert to Newton, and that will be 44 times 1000 all over the volume 6, and then we get the answer for this. Let's evaluate this now. This will give us 7333.3 Newton per meter cube. Okay, the next one now we're asked to get is specific mass. Well, since we've gotten our specific weight is equal to density times gravity. And so we can look for density. If I make density solve the formula, we have it will be equal to specific weight over gravity, and that would be 7333.3 over 9.81. That's the value for gravity, and that will give us 747.5 kilogram per meter cube. The next thing we are looking for here is specific volume. But remember now that specific volume is 1 over density, since we've gotten our density. So that will be 1 over 747.5, and that will give us 0.00134 meter cube per kg. And lastly now, we want to get specific gravity. Well, we can use the two relationships. Any of them will give us same answer. We can say that specific gravity is equal to specific weight of the fluid now over specific weight of water. We've gotten specific weight of the fluid. That's the first thing we did. That's 7333.3 divided by 9810. This will give us 0.747, or it does not have units. Specific gravity does not have units, because this is measured in Newton per meter cube, this is measured in Newton per meter cube. They will eliminate each other. Or we can use density to still solve this question, and then we still have same answer. We also know that or specific gravity is density of a fluid over density of water. We've gotten density of fluid to be 747.5 divided by specific density of water is 1000, and that will equally give us 0.7475. That's that for this question. We take example 2 now. Example 2, calculate the specific weight density, and specific gravity of 1 liter of a liquid which weighs 7 Newton. Okay, let's write out the given parameters here now. We are given the weight, 7 Newton, and we're also given the volume. The volume is 1 liter. But we have to convert to SI units now. So we divide by 1000 to get it to meter cube. That will be 0.001 meter cube. Now we have the weight and we have the volume. Now let's go to the first question, specific weight. Okay, so specific weight is weight over volume. Weight is 7, volume is 0.001, and that will give us 7,000 Newton per meter cube. The next thing here is the density. Well, since we have the specific weight, we can say specific weight is density times gravity. Then we can say density is specific weight over gravity. And specific weight is 7,000 and gravity is 9.81. So this will give us 7. The density is 713.5 kilogram per meter cube. Lastly is specific gravity. So specific gravity, let's use density. Density of the fluid, of the liquid, over density of water. And that will be 713.5 all over 1000. Density of water is 1000. That will give us 0.713.735. So that's that for this question. Example 3. Calculate the density, specific weight, and weight of 1 liter of petrol or specific gravity 0.7. We're giving specific gravity here 0.7. And now we are told that the volume is 1 liter, which is to meter cube divided by 1000. That will be 0.001 meter cube. Actually, 1 liter is 1 dm cube. So convert dm cube to meter cube is divided by 1000. So that's that about that. Now we can say specific gravity. We are looking for the first density. You can say specific gravity is density. Now this is petrol. So density of petrol over density of water. So we can say cross multiplying. We can say density of what? Density of petrol now will be equal to specific gravity of petrol times density of water. What specific gravity of petrol we are giving here to be 0.7 times density of water, that's 1000, and this will give us 700 kilogram per meter cube. We've answered that question now. Next is specific weight. Well, we know that specific weight is density of the petrol times gravity. So density of petrol, we've gotten that to be 700 times 9.81. And here we would have 6867 Newton per meter cube. Okay, and we asked next to get the weight. We know that specific weight is weight over volume. So if we cross multiply this, we get our weight is equal to specific weight times volume. What is specific weight? 6867 multiplied by volume 0.001, and this will give us 6.8 0.67 Newton. That's the weight of this fluid. So that's that for this. Viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. You see, as fluid flow, one layer or any layer causes shear stress on the layer adjacent to it, either above or beneath it. So the layer above causes shear stress on the layer beneath, and layer beneath causes shear stress on layer above. This shear stress actually is directly proportional to the velocity gradient, or directly proportional to the velocity with change in velocity with respect to y. Now, you see, let's derive the formula for viscosity. We have it that as we look at this now, this one fluid layer move the velocity u, and this layer above move the velocity of u plus du. We can now tell that the distance between these two layers is what we call dy. We have it that the shear stress between these two fluids is directly proportional with their change in velocity with respect to their distance between them. Then we can now say shear stress is equal to mu du dy. This du dy is sometimes referred to as velocity gradient, and this is shear stress, and this is mu, which stands for viscosity. So we can say this is shear stress, where tau is shear stress, change in velocity, distance between the fluid layers, and then this is mu, Greek letter mu, which stands for viscosity. If we make mu sort of formula, at times it's also called, dynamic viscosity. If we make mu sort of formula, we get that mu is equal to tau shear stress times dy over du. And the unit of mu, SI unit of mu is SI unit of mu is Newton seconds per meter square. So Newton's law of viscosity, it states that the shear stress on a fluid element is directly proportional to the rate of shear strain. The shear stress is directly proportional. So shear stress is directly proportional. This is what we call shear strain, which we also call velocity gradient. It also means shear strain. So if you remove the constant of the proportionality symbol, you put your constant of proportionality, which is viscosity, which is the formula we stated earlier. So, well, like I said before, that the SI unit for viscosity is Newton seconds per meter square, but it has other units such as poise, and the poise is just 1/10 of the Newton seconds per meter square. So whatever value you have in Newton seconds per meter square, divide it by 10. The answer you have will then be in poise if you are calculating viscosity. Another type of viscosity, we have another type of viscosity. This viscosity is actually known as dynamic viscosity, or you just say viscosity. But there's another type of viscosity known as kinematic viscosity. It's just the ratio of dynamic viscosity with density. When you divide dynamic viscosity with density, you have what we call kinematic viscosity, and it's denoted with letter V. So V is equal to dynamic viscosity all over density. Let's take some examples on viscosity. A plate 0.04 millimeter distance from a fixed plate moves at 1.2 meter per second, which causes a stress of 2.2 Newton per meter square on the adjacent plate. Find the viscosity of the fluid between these plates or between the plates. Well, given here, we are given the distance between the plates or distance between the top layer of the fluid with the bottom layer of the fluid or the layer beneath is given as 0.04 millimeter. We have to convert to SI unit now, so divide by 1000, and that will be 4 times 10 raised to power minus 5 meter. Again, we have our velocity, which is 1.2 meter per second, and then we have our shear stress, 2.2 Newton per meter square. So we can say that viscosity mu is equal to shear stress times dy over du, and that will simply be 2.2 times 4 times 10 raised to power minus 5 all over 1.2. So let's evaluate that now. 2.2 times 4 times 10 raised to power minus 5 divided by 1.2. So this is 7.3 times 10 raised to power minus 5 Newton seconds per meter square. Okay, we can choose to convert this to poise. So this will be equal to 7, that's just divided by 10, divided by 10. So just that's 7.3 times 10 raised to power minus 5 over 10. It will not be in poise. And that will be 7.3 times 10 raised to power minus 6 poise. So that's that for this question. 25 cm apart, the space between them being filled with oil of viscosity 14 poises. Calculate the shear stress in oil if upper plate is moved with a velocity of 2.5 meter per second. Well, to solve this, the first thing we are going to do is to bring out the parameter given to us now. The two plates are placed 1.2 cm apart. So we have that our dy is 1.25 cm. Dividing this by 100 to convert to meter, that will be 0.0125 meters. The next is we're given the viscosity 14 poises. Converting to SI unit now, that will be 14 times 10. 14 times 10. That will be 140 Newton seconds per meter square. Next is our velocity, which is our du, and that is 2.5 meter per second. So we can say we're looking for the shear stress, that's the required. So shear stress is equal to viscosity times velocity gradient, and that is viscosity 140 times 0.0125 all over 2.5. So this 0.7 Newton per meter square. So that's that about that. Now let's look at types of fluid. Well, fluids may be classified into the following. One, we have the ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. What then is ideal fluid? Well, ideal fluid are fluid which have no viscosity. But in reality, actually, there's nothing like ideal fluid because all fluid has viscosity. So then real fluid, these are fluid which possesses viscosity. So all fluid are real actually. Now we have Newtonian fluid. These are fluids that obeys the Newton's law of viscosity. I've given the Newton law of viscosity that states that shear stress is directly proportional to shear strain. So they obey the Newton law of viscosity. Their shear stress is actually directly proportional to their shear strain. We have the non-Newtonian fluid. These are fluids that don't obey the Newton law of viscosity. Then we have the ideal plastic fluid. These are fluids which shear stress is more than the yield stress and is proportional to the rate of shear strain. It's simply saying that their shear stress is though directly proportional to shear strain, but even when there is no motion, no velocity, they still tend to possess viscosity. And that's strange actually, because before you can have viscosity, there must be motion, there must be velocity, there must be a strain, a motion before velocity. But without that, they can still possess velocity. That's what simply an ideal plastic fluid is. We can illustrate all of this type of fluid using a graph, and I'll be illustrating that briefly. So now, this is the graph. This is the Newtonian fluid with a straight line showing you that shear stress is directly proportional to the velocity gradient. We have the non-Newtonian fluid. You can see that it's not a straight line, so it doesn't obey the Newton law of viscosity. Then we have the ideal fluid. It's ideal because despite the fact that there is motion between the fluid layers now, but there's no shear stress at all. And if there's no shear stress, there won't be viscosity. So this is an ideal fluid. And then we have the ideal plastic fluid, meaning that this ideal plastic fluid has shear stress even when there's no motion, when there's no velocity gradient at all. So these are the various type of fluid illustrated here. No need to express real fluid here because all fluid are actually real. So that's that about that.